This is Dario Kubler from ASIMOF Association. Good afternoon, good morning to Zibi Elizabeth Turtle. Welcome, and we are so pleased to host you today on this incredible event. We are going to have a very special speech tonight about an incredible mission, one of the missions that I think will change the history of humanity and a great discovery. But I'm not going to go into so much details because I will move the ball to my friend Jean-Marc Christil, my dear friends, and Andrea Bernagozzi from the Observatory of Valle d'Aosta, and they are co-hosting the event today together with the Le Pleiadi. So welcome again, Zibi, and Jean-Marc, is up to you to go on with the dances tonight.
Thank you, Dario. Thank you to everybody. Welcome to everybody. I'm very glad to have there Professor Turtle explaining us this incredible Dragonfly mission to the Saturn's moon, Titan. It's really important for us for having you there. So many thanks again for being there. And I want to bring the greetings from our administrative board, then from the municipality of Nus, and then from the Aosta region, autonomous region of Aosta Valley, that are three main founders of our astronomical observatory. And so, as Dario, I will not take so much time. I will let you the word, Elizabeth, and still many thanks to being there.
So now it's my turn. I am Andrea Bernagozzi. I am a researcher at the Astronomical Observatory of the Autonomous Region of the Aosta Valley. And my duty here is to tell a few words about the incredible scientist that is going to give a lecture to us this evening. And we are very honored and pleased to have such a great scientist with us tonight. Elizabeth Turtle, Elizabeth Zibi Turtle, has studied two very important schools and universities. She has studied at the Massachusetts Institute of Technology and the University of Arizona. And she has studied physics and planetary science. And she is a planetary scientist, one of the most important planetary scientists of our time. And she has worked in many planetary missions with the probes exploring our moon and the outer worlds of the solar system. She has been part of the imaging team of the Galileo mission, studying Jupiter and its moons, then of the Cassini missions, studying Saturn and its moons. And among these moons, there is also Titan, who is the subject of the lecture of tonight. She has been also a co-investigator with the Lunar Reconnaissance Orbiter. All these missions are has been realized by NASA, and she is also principal investigator of an instrument which will be included in the Europa Clipper mission. That is a mission that will study the moon Europa, moon of Jupiter. And obviously, she is the principal investigator. She has the main responsibilities for the science of this incredible mission, Dragonfly, who will going to study Titan, satellite of Saturn, in a very incredible way, with a very special probe, a lander, but also a lander that can fly. So I don't want to steal too much time, because the time of Professor Elizabeth Turtle is very precious, and we thank her again for sharing her time with us. So to all the people who is following this webinar, we are very pleased to introduce you Professor Elizabeth Zibi Turtle.
Thank you very much for that kind introduction and for the invitation to speak this evening. It's a pleasure to be with you virtually. in this new virtual world we're all inhabiting. I hope everyone is well and having a nice evening. So I will move to sharing my slides here. Okay. Yes, so I'll be talking to you this evening about the Dragonfly mission and about Titan, which is the moon of Saturn that we'll be exploring with Dragonfly, and what we'll be doing there. And you'll see here, I like to call attention to the fact that these endeavors are very much a team sport, as it were. And we have a very large team working on Dragonfly at this point. You see a subset of people here. This was obviously from quite a while ago now when we were all allowed to stand much closer together than we have been recently. The team has been continuing. We've been fortunate enough to be able to continue our work during the very challenging times that we're all facing right now. And this is from one of our virtual team meetings when we at least have been able to get together this way. So why do we want to explore Titan? It offers a very unique opportunity. We don't know how life came to form on Earth, and we can't go back and study our prebiotic history because things on Earth are overprinted by biology. So we look to places elsewhere in the solar system that can provide clues to the puzzle of the processes that may have led to life here on Earth. And in many ways, Titan is the most like the early Earth. And so it holds important keys to understanding chemical origins of life. So Titan is the largest of Saturn's 62 moons. It stands out here with its siblings in the Saturnian system, not only because of its size, but because you can't see the surface of Titan very easily at visible wavelengths. That's because Titan has an atmosphere, and this atmosphere has haze in it. We'll talk about in a few slides. So this atmosphere is quite unique, not only for the moons within the Saturnian system, but for any moon in the solar system. This is Titan again with its cousins in the solar system, and it's the only moon that has a dense atmosphere. And in fact, this is actually pretty unusual for planets as well. And so here again is Titan to scale with some of the planets and our moon and Pluto here. And Titan's atmosphere is actually denser than Earth's. The density of Titan's atmosphere at its surface is 4 times as dense as Earth's atmosphere at the surface here. And the pressure is 1.5 times. So it's actually the second densest atmosphere in the solar system of the bodies with solid surfaces. So that's one of the things that makes Titan a very unique place. So here's a few facts about Titan. Titan is the second largest moon in the solar system, just smaller than Europa, than Jupiter's Ganymede. The surface gravity at Titan is about 1/7 the gravity here at the surface of Earth, but the surface temperature out in the outer solar system is very cold. Titan's surface temperature is 94 Kelvin, or almost 180 degrees below 0 Celsius. So at these temperatures, the bedrock of Titan is water ice. And the atmospheric composition is actually primarily nitrogen, like our atmosphere, but then a few % methane. And this is where things get particularly interesting. The atmosphere is also very extended. So here on Earth, the top of the troposphere, the part of the atmosphere where most of the weather occurs, is between 10 and 20 kilometers altitude. At Titan, the troposphere is up at 40 kilometers altitude. So it's a much more extended atmosphere because of just the extent of the material in the atmosphere, but also the lower gravity at Titan. And then beneath the atmosphere, beneath the icy crust, there is a deep interior ocean of liquid water. So Titan, like many of the moons in the outer solar system, is an ocean world. So another thing that makes Titan particularly unique is the chemistry that occurs in the atmosphere. At the top of the atmosphere, the methane is broken down and it recombines, the remaining pieces of the molecules recombine to form very complex organic molecules, even in the upper reaches of the atmosphere at 900 kilometers altitude. And this material coalesces, forms the haze particles that make it difficult to observe the surface at visible wavelengths from orbit. And they fall out through the atmosphere where they cover the surface. And that's where things get even more interesting, because the surface is made of water ice. And there are times and places where that water ice may have melted. For example, at sites of impact craters where the target rock, in this case, water ice, will be melted by the energy of the impact. And now you have a warm pool of water that can be quite large and can persist for an extended period of time. And then there's the opportunity for these complex organic molecules to mix with liquid water for extended periods of time. And so that's what makes Titan chemically such a key destination for understanding the processes that may have occurred in the distant past on Earth in support of the development of life. Titan's and Saturn's year is quite long. So it's 29.5 Earth years for Saturn and Titan to go around the sun. And Saturn's axial tilt is a little more than the axial tilt of the Earth at almost 27 degrees. So Titan has very similar seasons to Earth's. In the northern summer, the South Pole is not illuminated at all. The North Pole is illuminated all the time, and vice versa in northern winter. Another aspect that is different in the time scale of Titan is that Titan's day is actually 16 Earth days long. Like our moon, the same face of Titan is always pointing at Saturn. Our moon, we see the same side of our moon all the time. And so its orbital period and its daily cycle are both the same at 16 days. So I wanted to put the past exploration of the Saturnian system into the context of this timeline of Saturn's year. So the Pioneer 11, Voyager 1, and Voyager 2 spacecraft, which flew by the Saturnian system between 79 and 81, all were exploring this system around the northern vernal equinox in Titan's year. And when the Cassini-Huygens spacecraft arrived at Saturn in 2004, it was several seasons later, just after the northern winter solstice, so late northern winter or late southern summer, when Cassini began its exploration and when the ESA-Huygens probe was released to study Titan. We'll talk about that a bit more as well. The Cassini mission was extended to persist through the equinox, and then extended again to persist through the northern summer solstice. And so this 13-year exploration of the Saturnian system is almost half of a Titan year or half of a Saturn year, which gives us an excellent baseline to understand how Titan's weather patterns, for example, change during the year. So I mentioned that at visible wavelengths, we don't see very much at the surface of Titan. This is a Voyager 2 image of the atmosphere. You can see the haze in the atmosphere up here above the limb. And it really wasn't until the 1990s that we actually started to get glimpses of the surface of Titan. So this is a near-infrared image taken by the Hubble Space Telescope that showed us features on the surface of Titan that persisted, that were always in the same places. So we knew we were seeing the surface. And here is another set of images from 2004 using adaptive optics from the Keck telescope, showing again bright and dark areas on the surface of Titan. So we didn't know what they were, but we knew we started to see the surface of Titan. And the Cassini orbiter shown here on the left, and the Huygens probe, shown here on the right, were designed specifically to study aspects of the Saturnian system, and in the case of the Huygens probe, Titan in particular. So Cassini had a dozen instruments designed to study all aspects of the Saturnian system, including Titan. And this feature here is the heat shield that protected the Huygens probe, the ESA-Huygens probe, as it came into the top of Titan's atmosphere. And the Huygens probe was designed specifically to study Titan's atmosphere and to make measurements of the atmosphere during descent through the atmosphere. And then if it survived to land on the surface, to study the surface as well. So as I said, Cassini arrived in 2004. The Huygens descent and landing was about 6 months later in beginning of 2005. And Cassini persisted in orbit for 13 years. And what this complicated diagram here is showing the orbits of the Saturnian moons, including in red here, Titan, but then also the trajectory of the Cassini spacecraft in the Saturnian system. There were over 120 close Titan flybys, and so we have a spectacular data set from which to learn, finally, the details of Titan's surface and Titan as a system. And this is, again, a near-infrared map compiled of almost 20,000 images taken by the cameras on the Cassini spacecraft. And you can see some of the same features, this bright area here, these dark areas here. You can see some of the same features that were apparent in the early Hubble Space Telescope and Keck observations. Cassini's cameras were designed specifically to be able to image the surface through the scattering in the atmosphere. Cassini also carried a radar, in fact, with components from Italy that allowed us to map the surface with a synthetic aperture radar mode. This is a different way of viewing the surface of Titan in these images, and you can see these strips that were taken during various flybys of the Cassini spacecraft over Titan's surface. In these images, the bright areas are rough at the wavelength of the radar, which is 2.2 centimeters. So at this scale, these features are very rough, and the dark features, especially these features, which we'll talk about in a little bit, are very smooth at that distance scale. And Cassini also had a visual and infrared mapping spectrometer that allowed us to get observations at different wavelengths, at different longer wavelengths out in the infrared. And from this, we were able to discern that there are different materials on the surface of Titan. But one of the major mysteries that remains after the Cassini-Huygens mission is that we do not know the details compositionally of these different units. So we know there are different geologic units. They show up here in browns and lighter colors and purples in this enhanced color view. But we don't know the details of the composition. The browns here are organic, and the lighter areas are also organic materials, and then the purple materials that show up here actually have a water ice component. But that's really the extent in some areas of what we know about the composition, and so that's one of the main outstanding questions that persists. But we do know a lot about the surface geology. And so I wanted to talk a little bit about that, because Titan is actually a surprisingly Earth-like place. And these dark areas that wrap almost all the way around Titan's equator turn out to be giant seas of sand. But on Titan, the sand is organic. It's a carbon-rich sand, as opposed to the silicate sand that we're used to here on Earth. Otherwise, the sand dunes are very similar to sand dunes we have on Earth. In fact, we have some very good analogs here on Earth that I'll show some images of later. So these are these dark features you see here wrapping around the brighter terrain. Again, this is a synthetic aperture radar image. So the dark features are smooth and the bright features are rough. These features are these longitudinal organic sand dunes. So basically, the largest Zen gardens in the solar system are at Titan's equator, out in the outer solar system. Titan also has impact craters. But like the Earth, there aren't that many. You can see a few here. There's one here. This impact crater that you're seeing another radar image of is this one, Synlap here. There's a very large one here that's almost 400 kilometers in diameter. But they're not that many impact craters. And that's something that's very similar to Earth. Again, on Earth, the impact craters get erased by active geology. And the same thing is true on Titan. There are active processes depositing material, for example, in the form of dunes. As we will get to, there is rain, there are fluvial processes. So there's a lot of deposition and erosion on the surface that modifies the surface and masks the impact craters, very much like the Earth. There are tectonic structures. They're what tend to be called mountains, although people, from a terrestrial perspective, mountains 1,000 or 2,000 meters high aren't terribly high. For an icy satellite, this is actually quite dramatic topography, and so we have these chains in places of topography of features that stand up above the surface. And again, you can see in this image as well the dunes wrapping around the higher standing topography. There are hints at Titan of cryovolcanism. So cryovolcanism is cold volcanism. In this case, the lava would be liquid water. So it wouldn't feel so hot to us compared to the volcano, for example, that's erupting in the silicate volcano that's erupting in Iceland right now. But on Titan, the lava would be water or a water ammonia mix. And there's a site here that's one of the best examples of a possible cryovolcano, where we have a large pit right next to a mountain. And the simplest way to explain that, as we see in many places in the solar system, including Earth, is possibly a volcanic feature with even flow-like features that are seen to emanate from this Sotra Patera right next to Dune Mons here. And then there are channels. Again, it's a surprisingly Earth-like geography on Titan. So this is an image taken by the ESA Huygens probe as it descended down through Titan's atmosphere, and these images of the surface were instantly recognizable as channels, fluvially carved channels, and the Huygens probe landed just here south of the equator. And not only are there channels, but there are actually lakes and even seas of liquid hydrocarbons on the surface of Titan, primarily at the poles. And so this is, again, a set of synthetic aperture radar swaths. And this is looking down on the North Pole. There are three very large seas here, Punga, Ligeia, and Kraken Mare. Ligeia is about 500 kilometers across, just to give a sense of scale. And then on the other side of the pole, there are all of these. There's a lake district with all of these very, well, not very small, but smaller lakes scattered around. And Titan has weather patterns as well. So the methane in the atmosphere plays a very similar role on Titan to the water in the atmosphere here. And so you get methane clouds, which are shown here in this near infrared image showing Titan's surface and the lakes and seas, but these very bright features are clouds. And you can see in this animation of images taken by the Cassini spacecraft, you can see the clouds. There's a little cloud here near the North Pole moving, and you can see the clouds here moving. This is in Titan's, near Titan's northern summer solstice, when the sun was high in the sky and the pole was illuminated all the time. And then the Huygens probe did survive to land on the surface and sent back this spectacular view of Titan's surface, of a gravelly plain with what are believed to be water ice cobbles. This is an image from our moon, but it gives you a sense of the scale of these features. And so these rocks are water ice rocks that look like they could be rounded rocks in the same kind of rounding we see of cobbles in terrestrial river channels. So we know that Titan has all of the key ingredients necessary for life as we know it. There's energy in the form of sunlight that drives this rich photochemistry at the very top of Titan's atmosphere. There are the materials that result, the very carbon rich compounds that result from that photochemistry. And these have the opportunity to mix with liquid water at Titan's surface in the past and in the present day in its interior water ocean. And then there's a second liquid in the system, which is methane, and the active methane cycle that Titan has, like our water cycle. And it's possible that liquid methane could support the development of exotic biological systems. And on Titan, we can study this chemistry in the context of a planetary environment with very Earth-like surface processes that transport and mix materials. So Titan offers us the opportunity to take the next step from Cassini-Huygens exploration to answer fundamental questions like what makes a planet, or in this case, a moon, habitable? What are the chemical processes that led to the development of life? And even has life developed elsewhere in our solar system? We don't know, for example, that we do know that in general, life as we know it is not terribly comfortable at 94 Kelvin. But we would be remiss if we did not ask the question if chemistry actually could have taken the step to biology in the past at Titan. And we know from the Cassini exploration where to go to look for answers to these questions. We know there are diverse surface materials, an Earth-like variety of geologic environments, and the scientific challenge became, how do we get instruments to multiple sites to be able to sample materials to measure the details of the composition? But here again, the atmosphere helps us out, because as I mentioned, Titan's atmospheric density is 4 times higher than Earth's, which means that flight is easier. The size of a wing or a rotor is smaller for a given amount of lift, and the lower gravity reduces the power required. So heavier than air flight is actually very efficient at Titan. And so that's why Dragonfly is designed as an octocopter. It's a rotorcraft lander, and this allows us to fly from place to place, to be able to travel wide distances over the surface of Titan, to be able to explore very different geologic environments. And Dragonfly will take everything with it, just the way the rovers, the Curiosity and Perseverance rovers on Mars do. We will take all of the instruments with us from site to site. But on Titan, as you see in the deployment and now the stowing of the high gain antenna from Dragonfly, we also need to be able to communicate from the surface of Titan. So Dragonfly will actually consist of a spacecraft, which includes a cruise stage that gets us from Earth to Titan, and then an entry vehicle, just like the Huygens probe, with a heat shield and a back shell here, and Dragonfly is tucked up inside. And then here is the rotorcraft itself. And this again is in the surface configuration with the high gain antenna deployed. Because we can fly, we can make measurements both on the surface and in flight. We can do aerial imaging. We can make profiles of the lower region of Titan's atmosphere. I mentioned that we do direct to Earth communication. We don't have the same infrastructure, unfortunately, at Titan that we do at Mars. We don't have a fleet of orbiters that can relay the data from Dragonfly back to Earth. So Dragonfly will communicate directly from the surface of Titan to Earth. And Dragonfly is designed to use an MMRTG. This is a multi-mission radioisotope thermoelectric generator. And this is the same power source that is used by the Curiosity and the Perseverance rovers on Mars. And for Dragonfly, we use this to charge our battery, and we use the battery power for flight and all of our science activities. The other benefit of the MMRTG is that it actually puts out a fair amount of what is typically called waste heat. But on a planet that has a surface temperature of 94 Kelvin, there is no such thing as waste heat. And we use all of that heat to keep the interior of the lander and the components at a nominal temperature to be able to operate. And I know we're all very familiar these days with drones. And so I like to show for scale, give a better sense of the scale of the Dragonfly lander. So this is me. And I know you don't actually know how tall I am, but I'm pretty average height. And I'm holding one of the prototype rotors. So this gives you a sense of the scale of the lander itself. So it's about the same size as the Curiosity or the Perseverance rovers at Mars, which gives you a sense of just how much physically easier it is to fly in the Titan environment, that we can take a vehicle this scale and be able to fly from place to place on Titan. Dragonfly is scheduled to launch in 2027, and this will get us to Titan in the mid-2030s. This is actually about 1 Titan year after the descent of the Huygens probe, which is very convenient because we're going to a similar latitude and we actually have direct measurements from Huygens of what the atmosphere is like at this time in Titan's year. We do direct atmospheric entry. We don't need to go into orbit at Saturn or Titan. We go straight into the atmosphere. We release the cruise stage and the heat shield protects Dragonfly as we go through the upper part of the atmosphere. We descend under a parachute. The heat shield drops off. And then as you saw in the video, Dragonfly will release from the back shell and fly to our initial landing site on the surface. And I know a lot of people are familiar with the same kind of entry sequence. The Perseverance rover just did this at Mars, and they talk about the 7 minutes of terror. But for Titan, it's actually a much more extended process. We have a lot more time to sequence all of the events that need to happen. They don't all have to happen in 7 minutes. We actually have about 2 hours from when we enter the atmosphere at 1,270 kilometers until we get down to the Titan surface. And this is the region that we're going to explore on Titan. So this is a region within Titan's equatorial dunes. Here is our approximate landing ellipse. And we have designed this to be south of the Selk impact crater. This crater for scale is about 80 kilometers in diameter. And so this gives us access upon landing to a wide variety of different materials, the organic dunes, the organic sand in the sand dunes, the interdune areas, the areas between the dunes, often have materials with a water ice component. And then the crater deposits themselves may be places where organics and liquid water have mixed. And so that gives us the opportunity to understand how far the chemistry could have progressed in that environment. So this is Earth. This isn't Titan, but these are some analog dunes, analogs to the dunes on Titan. This is the Namib Desert, where these same kinds of longitudinal dunes are formed, and they're actually about the same scale as well. So the dunes are 100 meters or so high. They're separated by a few kilometers. And you can see here on Earth that the dunes and the interdune areas actually are composed of different materials. So of course, on Earth, they're both silicate materials, whereas on Titan, the dunes have this organic composition and the interdunes can have water ice component. Another reason, though, for landing in the interdune areas near Titan's equator is that interdunes are very wide, flat places. And of course, from a landing perspective, that is an excellent area to find good landing sites. Dragonfly will explore Titan for a little over 3 years. This is 74 Titan days, or TSOLs, of operation, traveling up to 180 kilometers from our initial landing in the dunes to deposits associated with the impact crater and possibly even down into the impact crater. And we'll explore a couple of dozen unique sites along the way. And I should point out that the vertical scale here is very exaggerated. The dunes are about 100 meters high, and the horizontal scale here is about 200 kilometers. So it's actually, like for many icy satellites, quite subdued topography. Dragonfly will actually perform what we call a leapfrog exploration strategy because because we can fly, we can actually scout out future landing sites. Again, we don't have the same infrastructure at Titan that we do at Mars, so we don't have global high resolution imaging at the same scale that we do at Mars. And so Dragonfly, from a given landing site, when we're flying from our current landing site to a landing site we previously scouted, we'll actually fly past that and scout out a future landing site or a potential future landing site before coming back to the next landing site. The 16-day Titan day I mentioned also allows us to have a pretty relaxed operation schedule. No one has to live on Titan time the way people have lived on Mars time during operations on Mars. We will nominally fly about once every other Titan day, so it's about once a month here on Earth. So most of our time is spent on the surface, making surface measurements, science measurements, and communicating the data back to Earth. And these science measurements are very multidisciplinary. So we want to understand the prebiotic chemistry, the kinds of components that are available on Titan, and the processes at work to produce biologically relevant compounds. But we also want to put that in the context of the Titan environment. So we want to measure the atmospheric conditions. We want to understand whether there are methane reservoirs at Titan's equator, for example. And we want to be able to constrain the processes that mix organic material with liquid water at the surface in Titan's past, or possibly in the subsurface ocean today. And then we also have the capabilities to search for chemical biosignatures. Again, we don't have reason to know that chemistry has taken the step to biology on Titan, but we have the capability to make measurements that would identify chemical evidence were there to be water or hydrocarbon-based biology, or to have been water or hydrocarbon-based biology in Titan's past. So we have a suite of 4 instruments and a sampling system, and I'll kind of step through each of these in detail. This graphic here just shows the different components, the different sensors of the different instruments, and I will step through the capabilities of each of these. The cameras in particular, which are shown in blue, I'll point out here because we have them distributed around the lander to be able to do forward imaging, downward imaging, and we even have 2 cameras up here on the high gain antenna. This is to take advantage of the fact that the high gain antenna needs to be able to move to track Earth, to point to Earth, to be able to send data back. And so by mounting cameras up here, we can also use the motion of the high gain antenna to be able to build up images and a panorama of the terrain around the lander. So we have 2 drills. This is the sampling system, and these will drill into the surface, and then we can use pneumatic transfer because we have an atmosphere on Titan to just suck the material up, just like a vacuum cleaner. And then we bring that into a mass spectrometer. This mass spectrometer has 2 different modes. There's a laser desorption mode you're seeing here, which allows us to measure the compositions of the different materials on the surface. And then there's a gas chromatography mode as well. And that mode allows us to, among other things, to measure the structures of the molecules. And one of the kinds of biosignatures we have is the handedness of molecules, molecules that are mirrored. And an abiotic system tends to have about the same amount of both of those handedness, but a system that has biological control is more likely to have one or the other. And so that's one of the ways we can look for evidence of biological control. We also have a gamma ray and neutron spectrometer. This instrument allows us to classify the surface materials beneath the lander at every site, every one of our landing sites. This measures the bulk elemental surface composition. And so by looking at the different amounts of different materials, in this case, carbon, nitrogen, and oxygen, we can determine whether the surface is rich in water ice, or an ammonia composition, or these Tholen materials that are these complex organic analogs for Titan surface materials. It also can help us to see if there's near surface stratigraphy, because we'd actually be able to sense water ice with this instrument beneath a shallow layer of organic material. And so that will help us to understand the nature of the surface beneath the lander. The Dragnet instrument, which is the Dragonfly Geophysics and Meteorology package, has instruments to measure atmospheric conditions like temperature, pressure, methane humidity, hydrogen abundance, wind speed and direction. And we can, of course, look for variations from place to place, from day to night, as well as doing measurements of the atmosphere by flying up to different altitudes. In addition to understanding Titan's weather, we want to understand the nature of its surface. And so we can constrain properties of the surface material, for example, the porosity of the surface, to understand how quickly methane rain, for example, would be absorbed into the surface. And then we have instruments that will allow us to infer information about the ice shell itself, including seismic sensors. The field of seismology, of course, has broadened greatly recently, with InSight measurements being made at Mars. And there's been a lot of work done to understand what the nature of seismic signals would be in an icy satellite where you have a ice shell over a liquid water interior, which is, or a liquid water layer in the form of the ocean, which is very different from the terrestrial planets, the structure of the terrestrial planets. So one of the things we want to do is to understand how seismically active Titan may be. And then I mentioned the cameras, so we'll have the ability to build up panoramas. These, again, are not images of Titan, but we'll have the ability to build up panoramas of images around the lander, as well as doing images ahead and below the lander, and then very high resolution imaging of the sites where we'll do the sampling. And so this is an example of that. We'll actually bring LEDs with us to illuminate the surface at different wavelengths, and that will help us distinguish between different types of material in the material that we're sampling. The other thing that we'll be able to do if we do imaging at night is to use near ultraviolet illumination from an LED to see if the surface organics fluoresce. Different organics fluoresce, as you can see here, with different colors. And so it could be quite an eerie observation of the surface of Titan, illuminated at night by UV light, to see if the surface is glowing. So we've been very busy. 2027, a launch in 2027 sounds far away, but it's going to be here before we know it. And so we've been very pleased to be able to continue work under the current pandemic conditions. This is a Titan chamber here at APL. This chamber replicates the temperature and pressure at the surface of Titan. And so we've been able to do testing here of various equipment. This is some of the testing of the sampling system. And then we also have been able to use some of the wind tunnels to do tests of the rotor design. And we've been able to do flight tests as well. So this video on the left is from a flight test of a scale model. This isn't a full scale model of Dragonfly, but a scale Octocopter. And the video on the right will show images from our navigation cameras, because Dragonfly will need to be able to navigate by itself on Titan. And there are a number of ways that we want to be able to share the excitement, not only of exploring Titan once we get there, but also the excitement of designing and building a system like Dragonfly to explore Titan. So you see an augmented reality model. Again, this is actually half scale, but an augmented reality model where we can actually interact and see Dragonfly as it will exist, and also use this as a tool to design components in the interior of the lander. So as I said, we've all been very grateful to be able to continue work on this very exciting mission, and we're just very excited and looking forward to exploring Titan in the 2030s. So thank you again. It's a pleasure to talk with you this evening, and I'd be happy to take questions.
Thank you so much, Professor Turtle. I am Andrea. Thank you so much. Thank you again for this incredible lecture and for the incredible work that you are developing at the Johns Hopkins University Applied Physics Laboratory. At the beginning of this connection, I was so thrilled to have you with us that I forgot completely to state your affiliation. So please forgive me for my memory, and forgive me also for my English, by the way. Okay.
Not at all. No, you speak
okay.
quite well.
And I want to recall that this webinar is possible thanks to the work of the Astronomical Observatory of the Autonomous Region of the Valle, of the ASIMOF Association, and of the Astroteam Le Pleiadi, the Pleiades in English, the stellar clusters. And this is a group of institutions of a group of institutions working together to provide, to organize initiatives like this one, where we can share with all the people who is interested this information about exploration of space and of the sky and so on. We have to thank also, from this point of view, our translator, Paolo Attivissimo, who is translating our meeting from English to Italian, and also Alberto Villa, who is directing this webinar from the technical point of view. And we have received some questions, so I will say some questions to you, and also Dario Kubler, who is president of ASIMOF Association, is going to ask you other questions from the public and also from ourselves, if there is the time, obviously. And you have talked about Dragonfly, stating that it's easier to fly on Titan, if I well understood, because of the properties of its atmospheres. And there is a question about the way in which Dragonfly can fly, a technical question about the choice of building an octocopter, if this is the right word to describe it. And Jacopo is asking, why an octocopter, that seems to be something related to a Spider-Man movie in a certain sense, and not a quadricopter? Which are the technical reasons for this choice? Thank you.
Yes, that's an excellent question. And Dragonfly is an octocopter indeed. It's actually an X8 octocopter, which means that instead of having 8 arms like an octopus, it has the 4 arms with pairs of rotors on each arm. There are a number of reasons for this. One is that Dragonfly needs to fit within an aeroshell, and this is a more compact design to have the 4 pairs of rotors than it would be to have 8 rotors. The 8 rotors provide additional lift, and this configuration also gives some redundancy. So Dragonfly would actually be able to fly with only 7 rotors, possibly with fewer rotors, depending. We couldn't lose 2, if 2 rotors cease to function on the same arm, that would be a problem. But if we lost 2 rotors on 2 different arms, we might still be able to fly. So that's another reason for this design, is the redundancy afforded by the pairs of rotors.
Thank you so much. So now the floor is to Dario for a question from him.
Yes, thank you, Andrea. And again, it was great to listen to your speech. My first question is about any possible cooperation with the Italian teams for this mission. You mentioned that on the previous mission, Cassini, there was some activities from the Italian Space Agency about the radar and also for the main antenna was developed in Italy. I'm curious to know if you're expecting or you're working with anybody outside the US and especially in Italy for this incredible mission. Thank you.
Yes, thank you. As you say, the Cassini mission had key instrumentation components, especially for Titan, from Italy, and the Huygens probe as well included Italian instrumentation. Dragonfly does have international participation. At this point, we are partnered with CNES, who is working on components of the mass spectrometer. And we are partnered with JAXA, the Japanese Space Agency, who are providing the seismometer based on one of the lunar A designs they had for seismometer. At this point, I do not believe we have Italian participation, but international participation is, is so important for these kinds of missions, and there, I would hope, would be opportunities for, for future participating scientists from all over the world to work as part of this mission.
Thank you, Andrea.
Okay. I have another question from France, and the question is, can you repeat if you have said it during the lecture, but if so, I've missed it, sorry. It's been already chosen the rocket that will be used for the launch of Dragonfly and for such an incredible journey to Titan.
Yes, so the selection of the rocket for NASA missions is a choice that is made by NASA, and it is usually made at a later stage in the mission. We're still in our preliminary design phase. So we have provided information to NASA regarding the timescale of regarding the trajectories that we would use for different launch vehicles, but that's a selection that will be made by NASA in the future.
Okay, thank you so much. Dario, there are other questions.
Yes, a curiosity from my side is about you and your decision to embrace this incredible career. So how come you decided at some point to start working in this incredible journey and developing your skills for the space explorations? What made you to take this journey and decision?
I've always had an interest in in astronomy. My father had majored in astronomy. One of my grandmothers knew all of the mythology of the stars, and so we were always looking up at the sky. And I grew up along with the Voyager spacecraft, progressing outward through the solar system and all of the exciting discoveries that were made along the way. And so I'd always been interested in astronomy. And when I got to university, I took several astrophysics courses, and then I also took some planetary science courses. And I was kind of drawn back into the solar system by the fact that we can get to the planets. We can get down to the surface of the planets. We can actually pick up the rocks and study them. And so it's so very tangible. And so that's what drew me to planetary science in the end.
Incredible, thank you. So great experience and fantastic decision. I would have loved to do the same, but at some point I decided to become an engineer, and that was one of the biggest mistakes of my life.
Oh, well, it's also it's also critical though. And one of the things I showed the picture of the Dragonfly team at the beginning, one of the things that's that I feel so privileged to be able to work on a project like this is how interdisciplinary not only the science that we will do is, but the mission itself. And for Dragonfly, we have an extra dimension of that, because not only do we need all of the normal spacecraft engineering, but we need aeronautics because we need to be able to fly in an atmosphere. And so, getting to work with this incredible group of people with all of these different skill sets, science and engineering, but also, right, the graphical designers who put together the image you see behind me and the videos and the augmented reality views. It really takes so many different types of skills and experiences to build this kind of mission, and so it's really a joy to be able to participate in it.
And I'm also expecting that in the near future there will be a huge involvement of a specialist about artificial intelligence and deep learning in order to be able to create these autonomous driving vehicles on a planet, because obviously you cannot send commands in real time from Earth, of course. And it's critical on Mars. I can imagine on Titan would be immensely so difficult. So yeah, those fascinating areas of development will be extremely important.
Yes, absolutely. And I didn't speak very much about that, but as you say, Dragonfly needs to be able to operate autonomously on the surface of Titan. The light time, the time for commands to travel from Earth to Titan is 70 to 90 minutes. And so, the entire Dragonfly flight, one of its leapfrog flights will occur in less time than that. And so Dragonfly, will need to be able to navigate. We use terrain relative navigation from images of the surface. It will need to be able to navigate itself, and it will need to be able to, to identify safe landing sites. As well. And so we have, LiDAR and radar capability, similar to a self-driving car, actually. There's been a lot of development in that area, and we're able to take that, leverage that development and apply it to exploration of Titan. But all of that does, all that entire aerial mobility for Dragonfly is implemented in an autonomous way. And so you're absolutely right. There's, there's another large area of development going on there.
And in fact, this was the question by Emanuele, who was asking about the artificial intelligence processes that will run on Dragonfly to allow this incredible machine to fly by itself. And there is also a question from Monica, who has noticed that kind of skates, I don't know if this can be the right word, that are under the Dragonfly, and that give to this probe the aspect of a sled. And so Monica is asking if Dragonfly, when landed, can move like a sled, and if in this case can also going up a dune or a hill or so on, and so on.
Yeah, so the Dragonfly has skids the same way a helicopter has skids, but they're not designed to be used on the surface. They're simply the landing legs, if you will. So all of Dragonfly's mobility will be in the air above the surface of Titan.
Thank you so much. Dario, there are other questions.
Yes, let me also translate some questions, helping you, Andrea, on this. I'm picking up this question from Giuseppe, Professor Erifanti. He's asking, due to the fact that it's so extremely difficult and rare to have those missions in the deep space, why you didn't pick up the decision or took the decision to have a lander and an orbiter to fly to Titan? and instead you choose to just have this Dragonfly mission only without the orbiter?
Right. Yes. So that's a great question. Because obviously being able to have two different assets in the at Titan would really expand the capabilities of a mission. And indeed, there have been many studies of different ways to explore Titan, and a number of them, including some joint ESA-NASA studies, have looked at what you'd be able to do if you had both an orbiter, or perhaps even three components: an orbiter and a lander and a balloon, for example, to explore the atmosphere. For Dragonfly, Dragonfly is a New Frontiers mission. So this is a NASA mission class, the same class of mission as the New Horizons mission that flew past Pluto, the Juno mission that is at Jupiter right now, and the OSIRIS-REx mission that is bringing a sample back from the asteroid Bennu. And so these missions have this class of mission has a cost cap. And so all of the mission activities have to be able to be performed within a certain cost. And if you have multiple elements, it becomes much more expensive. And so Dragonfly is able to be a New Frontiers mission because we can have everything combined into a single element. And bring everything with us from place to place on the surface of Titan, and do the communication directly from the surface. We would love to have an orbiter. It would be spectacular to have a relay orbiter, for example. And there's a lot more science you can do from orbit at Titan. And so we of course would love to do that, but that does not fit within the mission constraints of the New Frontiers program. So we'll have to look to future opportunities and future missions for that kind of exploration at Titan.
Thank you. Yes, so it's a complex and compact and low-cost mission, so you can say.
Yes, yes, as it were.
Andrea?
Okay, talking about information and data transfer from Titan to Earth, and Emanuele is asking if you can say something about the data rate that you are going to achieve for the transmission of the important information from Titan to Earth, that obviously we hope, everybody hopes, that can be a very incredible quantity of information that will be needed to be communicated.
Yes, so this is another area in which we are completely spoiled by Mars exploration, by not only the proximity of Mars, but the ability to have relay orbiters. The data rate from the surface of Titan is much lower than the data rate that is possible from a Mars rover with a relay satellite. And so yes, so we'll have to content ourselves with a more limited amount of data coming back from Titan. But there is so much information that we will be able to gain from even a more limited data set. And there are so many, there have been so many developments in compression of data, for example, and selection of images, so we can play back, lower resolution thumbnails, for example, and then choose which images to play back at higher resolution because they have the most interesting features. So it is going to be quite a challenge managing the data volume, because every bit will be very important. But yes, we'll have to content ourselves with a lower data rate than we are perhaps used to.
Okay, thank you so much for this answer. Dario, from your side, do you have any other questions?
No, I don't. I think we addressed all of them, right?
Yes, it seems so also. So may I put my question to Professor
Oh, yes.
Thompson? Okay.
And then we have to say a big thanks to Andy.
Obviously, yes. It's in my plan, don't worry. Thank you so much. And so my question is about astrobiology. because when you, at the beginning of your wonderful lecture, I explained the objectives of studying Titan. You have talked about, for example, studying this world, this outer world, to understand in which way life can be born on our planet, in which way life has arisen on Earth. Okay, so do you have personally a role in the astrobiology studies that Dragonfly will perform? Or in which way this data arriving will be analyzed from the astrobiological point of view? Thank you so much.
Yes, that's an excellent question. There are a number of different measurements we can make to understand the astrobiological potential of Titan. I myself am not a chemist or a biologist. I primarily study surface processes, the processes of ice shells, impact cratering, and even the weather on Titan. But I'm not a chemist or a biologist, so take that into account perhaps as I answer the question. There are a number of different aspects of the chemistry of Titan that we want to understand. We want to know, first of all, what ingredients are there. What ingredients are there to be able to combine to form compounds that may be relevant to a biological system or to the development of a biological system, things like amino acids or proteins. Another thing we want to do is to understand how they differ from place to place. And so have, for example, in the interdunes where there may be water ice, but this ice would never have melted. So it's been in contact with organics, but if it hasn't melted, then you wouldn't expect, for example, as complex, organic synthesis to have occurred. But by comparing what we find in the dunes and in the interdunes to what we find in an environment like an impact crater, where we may have had, or where the organics may have, persisted within liquid water for extended periods of time, that will tell us, how much, organic synthesis can happen under this kind of condition in these kind of environments on Titan that we know have all the ingredients necessary for, for prebiotic chemistry. Understanding what has formed and then the processes that have enabled that those ingredients to form is really key. On the other side, on the side of detecting, or searching for biosignatures is a better way to put it. There's been a lot of research over the last few decades in, of course, astrobiology, as you say, and understanding in particular what kinds of signatures or what kind of measurements could provide evidence of biological control of a system compared to chemical control of a system. And so, for example, on the NASA website, the astrobiology website, there's a ladder of life that has all sorts of different measurements and what kinds of information the different techniques can provide. And so what we want to do with Dragonfly is take advantage of the opportunity to make different types of measurements that would provide insight as to whether there could be biological control of the system. And so I mentioned the chirality. If there's a chiral preference, for example, that can be a strong indicator that there is biological control with a preferential molecule structure as opposed to chemical control. We can also look at the distribution of the different complex molecules. If you have kind of a gradational distribution, again, it's more indicative of chemical control of the system. If you have very specific molecules that are preferred, that again can be an indicator of biological control. And then we can even, sense whether there are hydrogen sources and sinks. And that too can be a signature that there is something actually generating or absorbing hydrogen. So we've designed the mission to have a number of different types of measurements that we can make to be able to get at that. Because of course, if you have one, you always want to, for that kind of information, you want corroboration. And so we've designed it to have multiple ways at getting at the possibility of detecting biosignatures. But of course, primarily the mission is about the prebiotic chemistry. And so really that's what we want to understand in the system, and the possibility of and the potential for this kind of chemistry that far out in the solar system.
Thank you. My question was also triggered by the way that our astronomical observatory is being involved in a project about exoplanets, so not planets or moons in our solar system, but outside the solar system. And so also our little astronomical observatory of the smallest of the Italian regions is part of the community at large of who is involved in the astrobiology studies. And from this point of view, we are organizing in July a summer school devoted exactly to astrobiology. And from our point of view of the Astronomical Observatory of the Autonomous Region of the Aosta Valley, your lecture is also a step towards our summer school of astrobiology. So thank you so much. Dario, maybe there is a last minute question by Monica.
Sorry, I didn't check. In the meantime, just let me take this opportunity to ask to Zibi. I know it's a still ongoing research and development on this incredible mission, but what's next? What do you expect we will see after we all believe will be a great success of this mission?
Oh, what's next after Dragonfly? Okay, I thought you were asking at first what's next for Dragonfly, because we of course have many steps to go before we get to Titan. There's so many things that the Titan environment is so rich, and there's so many other questions, and I'm sure like every mission we send, Dragonfly itself will spawn new questions that we probably can't even some questions we may not even be able to imagine right now. But Dragonfly will explore a very specific region, carefully targeted near Titan's equator and near an impact crater because of the astrobiological potential of this kind of site on Titan. But that's only a piece of the Titan system. And so there are, as we talked about, orbiters would be able to do measurements at a global scale to, help us to understand more about the ocean in Titan's interior. Also, there are those incredibly intriguing lakes and seas, especially at Titan's North Pole. The liquids are primarily at the poles and primarily at the North Pole. The timing of the New Frontiers mission, this New Frontiers mission, is in this launch window, arriving at Titan in the mid 2030s. It will be northern winter, and so the North Pole of Titan won't be illuminated, which means that it's harder to explore Titan at the North Polar region at this time. Also, because we're doing direct to Earth communication, and if the sun isn't up in the sky, neither is the Earth, and so we wouldn't be able, even if we had an opportunity to send a probe at that time of Titan's year, we wouldn't be able to get the data back from the surface of Titan. So the lakes and seas are certainly an area of very high interest, and we'll have to wait to another future mission to explore those in detail.
Great, thank you.
Okay, there are two other last-minute questions now. Monica is asking if the data will be analyzed only in United States institutions, or if in the framework of your international collaboration, the data will be released also to other institutions outside the United States.
So the science team is international, and so so there will be international participation in the analysis of the data from Dragonfly, and all NASA planetary mission data is made public, is archived in the NASA planetary data system, and Dragonfly data will similarly be archived in the planetary data system, and thus be available to everyone to be able to explore it.
Thank you. And Rodri, and this is the last question, then we are going to thank you for your lecture and finish our webinar. Rodri is asking if there are other moons that are interesting as much as Titan for a mission that can be similar to the Dragonfly probe with a drone flying over their surface and so on.
So there are not many places in the solar system that are that have this kind of atmosphere. Dragonfly, exploration will be fairly, and among the satellites, certainly there are not other moons with atmospheres, and so Dragonfly is pretty specifically designed for Titan exploration. As you may know, they did with the Perseverance rover. It brought the Ingenuity helicopter, and it was so exciting to get to watch that take its first flight and several subsequent flights on Mars. Mars has a much more challenging atmosphere to fly in than Titan does, but but flying is certainly a possibility in the Martian atmosphere. And flying in the upper reaches of the Venusian atmosphere as well would be a very interesting exploration strategy. But in terms of the moons in the outer solar system, unfortunately, they do not have, most of them do not have atmospheres. And so we would not be able to use flight as a way to travel from place to place on those moons.
Perfect. So we have also, obviously, a lot of congratulations to you for your mission, but also to you personally for the way in which you have lectured us about this incredible adventure, this incredible journey of Dragonfly to Titan. And about this journey, as Dario was saying a few minutes before, we have also to thank a lot Andrew Driesman, who is, please Elizabeth, correct me if I'm wrong, is the managing executive of the space exploration sector at the Johns Hopkins University Applied Physics Laboratory. And we have been very lucky to meet him, Andrew Driesman, and his wife Amber during an initiative that our astronomical observatory together with the autonomous region of the Valle and ASIMOF, and Dario Kubler, I remember, is the president of ASIMOF. We have met Andrew Driesman and his wife Amber during an initiative devoted to celebrate the 50 years of Apollo 11 mission. And this is for me also the occasion to say good luck to Dario Kubler and all the friends of ASIMOF, because if I'm not wrong, tomorrow they are going to celebrate another important anniversary of space exploration, the 60 years from the flight of Yuri Gagarin. Obviously, the exact anniversary was in April, but due to the pandemic, it was not possible to organize a public event, and they are going to organize a public event tomorrow. So we have been very happy to host you, Professor Turtle, and let me say that your smile and your enthusiasm when you were talking about Titan, the mission, and there are so many things to explore. You have said a certain point. Your smile, like your smile that you are doing now, I think that can be an incredible source of inspiration to other people and also to young people to study astronomy, astrophysics, physics, planetary sciences, astrobiology, and all these sciences that can understand, that can help us to understand how life has evolved here in the solar system and maybe in the rest of the cosmos. So from my point of view, Andrea Bernagozzi, researcher at the Astronomical Observatory of the Autonomous Region of Valle, this is everything I wanted to say. Now I give the floor to Dario from the greetings from his side. Thank you so much, Professor Turtle.
Thank you.
Yes, so great. It was a great pleasure, and we learned a lot. And as Andrea stated, your clearness, but also your empathy, your smile was incredible. So it was a privilege for us to learn from you, and we wish you a very big luck for the rest of the exploration and development of this great mission. And of course, we will stay in touch. We want to know what's going on and how you're going to achieve this incredible goal. So again, thank you, Zibi. Thank you, Andrea. Thank you, Professor Andy. And I wish you a very nice day, a great evening to everybody on the audience. Let's hope that Italy will win tonight, of course, for the one who loves soccer. And
sorry, everybody has his own 2 hours of terrors. Who Titan, and there is someone that has the hour of terrors here in Italy. Okay.
And thank you for remembering the big event tomorrow with the unveil of the Vostok capsule. And the great news is that we have been asked by NASA to rent our capsules for an exhibition called Space Adventure, which is running Europe at the moment. So we are glad to be part of this NASA adventure from Italy. Ciao. Thank you.
Thank you so much. It's
Bye
been
bye.
a great pleasure.
Thank
Ciao,
you.
Andrea.
Ciao a tutti e a tutti.
Ciao a tutti. Buona serata.
Take care.